This presentation is based on solvent-free migratory insertion reactions. The general reaction of migratory insertion can be seen here, and the following rules apply. Ligands X and Y must be cis to one another. Ligands must have pi bonds present, for example carbon monoxide ligands. Ligand insertion is reversible and the back reaction is known as beta elimination. And there should be no change in the metal oxidation state prior to and after migratory insertion. Let's consider this metal complex and work out its electron count and oxidation state using the covalent method. Both methyl and cyclopentadenyl are anionic -1 ligands, leaving molybdenum with a +2 oxidation state. Molybdenum has 6 valence electrons, which means it contributes 6 electrons to the complex. The C5H5 ligand contains 5 electrons, the carbon monoxide contributes 2 and there's 3 of them, so totals 6 electrons, and the methyl contributes 1 electron. This gives a total of 18 electrons, which is what we would expect. Now let's discuss the structure and bonding of our complex. The complex is trigonal bipyramidal because it has 5 bonding pairs and no lone pairs. Our cyclopentadenyl ligand is a pi donor. Our carbon monoxide is a sigma donor and a pi back bonding ligand. And our methyl is a sigma donor. Below shows a mechanism of a migratory insertion reaction followed by decarbonylation. The carbon monoxide ligand inserts into the metal ligand bond, in this case between the metal and the methyl ligand. The arrows show the movement of electrons that lead to formation of a new metal carbon bond. The original ligand, which in this case is carbon monoxide, can be displaced by another ligand. So in this case, the carbon monoxide is displaced by a phosphine ligand. After migratory insertion occurs, other reactions such as decarbonylation can occur, as shown in this mechanism, and the resulting product should lead to a complex with the same oxidation state on the metal. Now let's just confirm that our migratory insertion reaction mechanism follows the expected rules and remains with the same oxidation state on the metal. As we can see from the picture below, the metal remains as a +2 oxidation state due to the -1 charge on the methyl ligand and on the cyclopentadenyl ligand. Now let's discuss ways in which we can study the reaction of metal complexes to determine how the reaction has proceeded and if it's reached completion. Like most things, we can use IR spectroscopy to study the reaction. We do this by monitoring changes in stretching frequencies. Electron withdrawing groups are worse sigma donors and better pi acceptors. This leads to reduced electron density, which further leads to reduced back bonding into pi star orbitals. This results in stronger bonds and therefore increased wave number. In this case, the complex prior to migratory insertion will have greater stretching frequencies as it has an extra carbon monoxide compared to a phosphine ligand, which is more electronegative. We can also use NMR spectroscopy. So, there are different types of NMR spectroscopy. Hydrogen and phosphorus are commonly known. So in the case of our complex, we could use the phosphorus NMR to determine whether or not the reaction has reached completion, because the starting complex does not have a phosphine, whereas the finishing product does have a phosphine present, so there would be peaks present in a phosphorus NMR. Also with hydrogen NMR, the methyl group will be at different chemical shift depending on how de-shielded it is. So in the first complex, we have more carbon monoxide ligands than we do in the second complex. This will de-shield the hydrogens more and therefore will give a higher chemical shift value. We can also use high pressure autoclave experiments. These promote insertion of carbon monoxide to metal centres and you monitor the pressure and ensure a correct amount of carbon monoxide is available for insertion.